technology. Today, we have the 6 speakers from Chinese Association for Science and Technology, and we also have a manager from the cast, China cast, Yang. And firstly, I would like to invite Professor Yang to give a welcome speech. Thank you, Yang, please. Yeah, you can give a speech there.
Good afternoon, everyone, ladies and gentlemen, and friends from far away. Today, it's my great honor and pleasure to be here to attend the third meeting of the UN event. And I'm very glad that I have so many attendants, as well as 6 distinguished speakers from China on behalf of the China Association of Science and Technology. And the topic is to the climate change, adaptation, and the length of go away with the COP28. Now I give the microphone to the chairperson of the third event, Professor Wenjie, and thank you for doing everything and make everything happen.
Thank you, Yang, and we also thank the audience. This such events is we in person here, and also we the online use YouTube for all our colleagues and friends, in China and in other countries. We are focusing on the climate adaptation and resilience. In UNFCCC, most topics are related to the mitigation of climate change. But actually, climate adaptation, I think, is a long-standing topic. I think before the climate change issue emergence, humans understand the adaptation from Africa to Europe to Asia to all over the world. And also in the future, even we have the carbon neutrality city, carbon zero world, but still, the climate adaptation issue will keep on because our climate system have its thermal inertia. Even the zero carbon world, the temperature will continue, go on. So the climate adaptation is a long-standing issue. And we should pay much attention on such an issue. And I just saw the march, in the outside of the meeting, it's hundreds of thousands of people is march there. And they said that half for the mitigation and half for the adaptation. This is for climate justice now. So this proposed why we, China Association for Science and Technology, to make a choice of such a system and this proposal of this meeting. So I would like first, are you ready? Wenxia? Yes, first we would like to invite Wenxia to give the first talk. It's on the climate change projection in the Guangdong, Hong Kong, Macau, Great Bay Area based on system model. She's a PhD student in the Sun Yat-sen University. This university is in the Hong Kong, Macau, and Guangdong. It's in the Great Bay Area. Yeah, please. You have 10 minutes.
Okay. Good afternoon, everyone. I am Qianggong, a PhD student from Sun Yat-sen University. On behalf of my supervisor, Professor Wenjie Dong. I'm honored to present our work about climate change projection in the Guangdong, Hong Kong, Macau Great Bay Area based on a high-resolution regional Earth system model. We call it CSIM. Please wait a second, thank you. Thank you. So, as an important hub of China's opening up and a leading driver of economic growth, the Guangdong, Hong Kong, Macau Great Bay Area is recognized as one of the world's 4 major Great Bay areas, alongside the New York, San Francisco, and Tokyo. Compared with the other 3 Great Bay areas, the GHM Great Bay Area shows unique characteristics considering its space, population, and GDP scale, as well as the economic influence. However, located on the south coast of China, the GHM Great Bay Area shows frequent meteorological and oceanic disasters. And besides, due to its high urbanization, the high density of population, and the prosperous economy, the GHM Great Bay Area shows sensitive response to climate change. And the climate characteristics of the GHM Great Bay Area pose challenges for the regional climate change mitigation and adaptation. However, the traditional CMIP6 models do not possess the capability to accurately simulate climate change in the GHM Great Bay Area or other highly refined regions. So it's urgent to develop a new generation of the ocean and atmosphere ecology and human regional Earth system model. And this model should have the ability to achieve the variable super high resolution with unstructured grid. And it should also realize the seamless integration of the weather forecast and climate predictions. Besides, we hope it can achieve a two-way coupling between the human and Earth system. Based on the development goal of the Earth system, Sun Yat-sen University has developed a new generation, the Global China Sea and the South China Sea offshore, the three-layer listed and unstructured grid ocean model. And this model based on the supercomputer, the Tianhe. To resolve the complex irregular coastal geometry and the islands in the ocean, the most effective way is to develop an unstructured grid. The international has tried some attempts for the unstructured grid, such as the finite volume cube sphere dynamical core developed by GFDL. As for our system, it employs the triangular unstructured grid. You can see from the left top two panels. Compared with the structured grid, the unstructured grid can fit the coastal lines very well. And compared with the CESM with the traditional structured grid, our system model is capable of reproducing the marine dynamic process and the near shore area, which cannot be analyzed by the CMIP6 model. And we can compare these two panels. So based on the use of the unstructured grid, the system can achieve the ultra-high resolution, and the highest resolution is about 2 meters. We can see this panel. It shows that the system can simulate the currents around the piers along the Hong Kong-Zhuhai-Macau Bridge with a resolution about 2 meters. Besides, The system also takes good advantage of artificial intelligence. It added the disaster identification and the tracking module and the intelligent adaptive modeling system. With the use of the artificial intelligence, the system can identify and track the pace of a typhoon and automatically to increase the resolution of the grid around the pace. And this allows system to simulate the typhoon more accurate while controlling the computational expense. Overall, the system has achieved the seamless integration of multi-temporary and spatial scales for global, region, and king area, and also achieved the integration of climate simulation and also the weather forecasting. So we can use the system to simulate the regional climate change in the GHM Great Bay Area. So firstly, we use the SIMIF6 dataset as the boundary conditions to drive the system. In this way, we can dynamically downscale from 100 kilometers to 9 kilometers. And this slide shows the variables in the SIMIF6 that used for the dynamic downscale. And this is the simulation result. We found that the sea surface temperature over the South Sea is projected to increase by about 3.6 degree by the end of this century under the highest emission paceway. And we further downscale from the regional resolution of 9 kilometers to the estuarine resolution of about 2 meters. This way is for the purpose to project the trend of inshore flooding in the Great Bay Area over the next 100 years. And this is the simulation result. Based on the evaluation of the coastal inundation around the GHM Great Bay Area, we found that at the end of the century, the area of inundation increased by 25% compared with 2020. And at the end of century, there will be another 14% increase compared with the middle century. Okay, so overall, to better respond the regional climate change in GHM Great Bay Area, Sun Yat-sen University has developed a new generation high-resolution regional Earth system model. And this model has achieved the super high resolution with unstructured grid, and also the seamless integration of the weather forecasting and climate projections. Besides, it also combines artificial intelligence technologies. And we hope that with the use of this model, we can meet the needs of disaster prevention and mitigation for the Great Bay Area development. And finally, we hope we can use this model to achieve the aim that the first-class Great Bay Area. Thank you.
Yes, thank you, Wenxia. Good timing. And Wenxia is a very young PhD student. Her generation is our future. So I think the next speaker is Panmao Zhai. He is the co-chair of the IPCC R6 Workgroup 1. And also he is selected as 100 important person by Times this year and the last year, 100 person in this, our Earth. So, Panmao, please.
Thank you, Professor Tong. Dear colleagues, friends, very glad to take this opportunity to give a report based on our own research and also IPCC results. So my topic is try to talk on the risks and how we handle for the extreme weather and the climate events in the urban areas. Next, please. Okay. Say, here we see, firstly, we look at the right side, left side of the figure. We see IPCC reported as global mean surface temperature during 2011 to 2020 is something 1 degree, 1 point Celsius for global mean surface temperature above the early 19th century, later 19th century. However, the increase of the land temperature and sea surface temperature are different. We see here, land temperature increase is about 2 times compared with sea surface temperature. So all the cities we know located in the land area, and also city has added additional effect from urbanization. So, and the global warming background and urbanization background, climate change in city really very significant. And right side, you see the figure is some, the background temperature increase in different cities. And really, this is a trend only from 1958 to 2018. That's, you see, under the warming background, the city local temperature increase really a lot. And based on our, the 2019 paper published, only cited, you see the temperature, the hot days. We say the hot days, the heat wave days, something like 35 degrees Celsius. And if we counting the number of days during the recent 20 years compared with the previous 30 years, you see all the mega cities in China. Mega cities here used something like 10 million, over 10 million population. You see almost other cities, in the past have fewer hot days, now almost doubled compared with 30 years ago. And some places like Chongqing, Wuhan, along the Yangtze River, in the mid and above the Yangtze River reaches, the hot days something like already reach 1 month. That's really very significant increase in the extreme hot days. And also we found not only influence the daytime temperature, but when we look at the nighttime temperature, we put extreme hot daytime temperature and nighttime temperature together. We call that as a composed day-night extreme event. That's, you see the exposure areas in China, the red curve you can see, increased very, very significantly. This is only up to 2015. If you put recent 7, 8 years, you will see more increase of the compound day-night hot events. And we try to look at different areas, like in the capital city area, we call Tianjin, Beijing, and Hebei in the region, and all the Yangtze Delta region, and also in the upreach of the Yangtze River and the Pearl Delta region. You see the urbanization really is, you can see very clearly the growth very quickly. And also, we try to, to detect the compound events in the urban, rural, and different. You see the figure C, really see the difference in these city regions. And also the curve you see, the green line is something like for the rural area. However, the red curves is for the urban area. You see, urban area really have much more increased trend compared with the rural areas. Last year, the summer in China along the Yangtze River Valley, we experienced the most severe the heat wave events. And we see all the circled regions are all the megacities. And the final one, the figure D, we listed the compound events, both day and night time create the record, the heat waves there, the frequency much higher near the Shanghai region and also another in the Hubei area and other one in the upreach of the Yangtze River, Sichuan basin. And we try to, to attribute the compound hot extremes to the human activities, greenhouse effect, greenhouse gases, aerosol effect, and urbanization. Clearly, we can attribute something. GHG, greenhouse gases contribute the most, and the urbanization contributed about 1/3 of the frequency of the compound hot extremes. Aerosol effect is something like 10% stronger in the cities. So in the future, if the air condition is going to improve, then become less polluted, then it seems something like future. The compound extreme can increase. And also, such of the extreme event linked to the modality, of the people in the cities. We see here, compound events really play a more important role in the modality. Especially you see the total number, the blue signs are all for the compound events. For gender, age, you see all can detect such of the influence to the people's modality. And here's a day-night compound heat waves brings something like 10 to 20% higher modality rate as compared that of the day-night extreme only. And also, hot climate can intensify the ozone pollution. So compound hot and ozone extremes are related to climate background in the urban China, especially you see in dry cities, cities in the dry area and in the moisture areas, they have different, there are some difference. So dry areas normally have, we have more ozone climate penalty, and also related to the population in the city. IPCC census report also, say global warming also can exacerbate heat, humidity, the compound risks to human health. So related different degree of warming, you can see different distribution. And in the world, normally something like for the tropical area have more stronger influence by the heat, humidity risks. And also the combination for the cities, combination of future urban development and the increasing frequency of extreme climate events such as heat wave will, exacerbate the heat stress in the cities, and the urbanization will intensify urban heat island effect in addition to the change in the background climate. So to adapt to the adaptation and the socio-economic pathways will affect the level of climate-related risks. If we have limited adaptation, you see much higher risk. But if we have proactive adaptation, you see the risk will be greatly reduced. And urban areas are the main source of climate forces, as well as the site of innovation and the solution for adaptation, mitigation, and sustainable development, because urbans, release most of the greenhouse gases, and also urban will have best science knowledge and also have leadership there. So from IPCC point of view, urban can be there, find the best solution to address climate issue. And strengthening resilience and adaptive capacity to climate-related hazards in cities are extremely important in coping with exacerbating risks of climate extremes. My talk will be here. Thank you so much.
Thank you, Panmao. Thank you for your shares and your discoveries from IPCC AR6. And our next speaker is Professor Jiang Tong. He's from the Nanjing University of Information Science and Technology. And he is the newly selected member of the Academy of European. In China, we have around 2,000 Chinese Academy mission of China Academy of Science Academy members. But in China, we only have 10 members of the Academy of European. So Jiang Tong, now, please give only 10 minutes.
Good afternoon, and it's a great honor to be here. Was invited by organizer to have a talk about adaptation, and as we know that we have used the shared social economy pathways in the IPCC AR5 and AR6. Now I would like to present here this new thought or new idea which we are missing in last 6 round of IPCC report is we named shared adaptation pathways. And I will show you this. Next one. And as we know, the last 35 years, IPCC published 6 rounds of the IPCC assessment reports, 11 special reports, and 5 technical reports, and 6 guidance for methodologies. And I'm great honor to be in the starting working for IPCC in 2007, which the end of the Copenhagen agreement, and in 2007, and last AR5 and AR6, I'm as leading author to working for this, and nearly 15 years for working for IPCC reports. And from this table, these figures, the center point is IPCC during the last 35 years, they developed different scenarios. Somebody or scientists think that scenarios is so important for the IPCC report, like yeah? If we developed a new, very accurate scenarios, it would be better for the assessment report for future projection. And in 1990, we developed scientific assessment 90, the first scenario used for IPCC AR first assessment report. 5 years later, when they published the second assessment report, and it's named new scenario is the IPCC scenarios 92. 5 years later, and until from TAR and until AR4, there's a special report on emission scenarios, which we are mostly the old people, scientists know AR A1, A2, B1, B2. Later on, in AR5, most climatologists like to using representative concentration pathways, and it's RCP scenario. It's very popular used for the research. In AR6, most people coming from impact study and adaptation and mitigation field, they would like to have socio-economic pathways, and we developed for this. And let's see. This is a IPCC latest scenarios from the bottom, from this. Yes, the beamer could not work. From the x-axis is the RCP scenarios, and from y-axis and x-axis is SSP scenarios. This means from the RCP and composed of the social economy scenarios together. Then the color shows that the CMAP6 experiment based on these tables. Then they're still missing up to now is is adaptation scenarios. I make marks here. Is adaptation scenarios is missing, and I should in last several years I'm working for the new scenarios, shared adaptation pathways. As we know, the SSP scenarios plus RCP plus SSP is new SSP scenarios. We are working for the very popular for these tables. They're working for the CO2 emissions and pathways, which CO2, which years, different ways and different pathways and different scenarios to provide it to local government or parties to be adapt, to be mitigate the mitigations. This will be provided to the government. Then, how they set up the SSP 1 to 5? We are considering this is one of the definition we published in the 2-degree report, glossary parts, and they could be including covered seven different aspects. First, they are covered populations and human resources, and economy and development, and human development, and technologies, and lifestyle, and environment and natural resources, and policies and institutions. All these seven aspects to be included in the SSP from 1 to 5. And how to calculate the in practice, yeah? And the projection of populations, and we're using PDE models, populations, development and environment models, to calculate from base year population in base year in 2020 and population development to input all the data to the models and to calculate the future assumption of SSP framework. And finally, we gave the localization of the parameters to calculate the future populations. And we also projection for the future economy, including we're using the Cobb-Douglas models to predict, to project the future economy change. All those informations we are made for the great data sets for population and economy. We are all free, published free of charge, published on the net, and free download from the net, and from 2 data bank. And we also have paper published in the scientific data, and can be probably used for the this for all these. Up to now, I check, yes. Up to now, and I check this is more than 30,000 is up download. For mitigation, I would like to show that this concept. The green one is adapt the current situation and the future. In the future is residual risk in the other colors and center white color. And then I developed the new concept for the social economy, shared adaptation pathways from 1 to 5. Then we can see the shared adaptation pathways and the residual risk and the current adaptation investment and highly reduced risk. And I also working for 2 cases, food security. We find it's different, more and more adaptation and the more food security. And we also have another case study for working for the residual risk and health investment for the dengue fever study. And we also developed 4 different types of the adaptation pathways. And during the pathways, we can think that improvement of adaptation capacity can significantly reduce the incidence of the dengue fever in Asia metropolitans. And more than 20% of the decreasing of the dengue fevers. So this is just idea and case studies for the shared adaptation pathways. Thank you for your attention.
Thank you, Professor Jiang. And the next speaker is Dr. Wenxia Zhang. He's from the Institute of Atmospheric Science, Chinese Academy of Science, a very important institute in China for the climate change study. Wenxia, please, 10 minutes. Hello? Yeah. It's black. Screen is black. Yes. Okay. Thank you.
Okay, good afternoon, ladies and gentlemen. It's a great honor to be here to share our understanding about the climate change over the high mountain Asia. And this story is about the drying South Himalayas in the past will get wetter in the future, associated with a reduction in anthropogenic aerosol emissions. And I'm giving this talk here on behalf of Professor Tianjun Zhou. The high mountain Asia consists of Tibetan Plateau, Tibetan Plateau and the surrounding Hindu Kush, the Karakoram, and Himalayan ranges. It contains the largest volumes of ice outside the Arctic and Antarctic. The high mountain Asia also feeds water to many Asian rivers, including the Yellow, the Yangtze, the Ganges, and the Mekong, etc. So it provides water resources to billions of people living in Asia. So it serves as the water tower of Asia. So the climate change over the high mountain Asia is of vital importance to the livelihoods of people living in this region. However, over the past decades, the high mountain Asia has undergone rapid climate change. The observed warming rate of the high mountain Asia is about twice as fast as a global mean. And apart from this prominent warming trend, the hydrological cycle over this region is also changing significantly. And the most prominent feature of the hydrological cycle change is the dipolar pattern of precipitation change. In particular, the precipitation in the central and northern part of high mountain Asia has increased over the past 4 decades, but the precipitation in the southern high mountain Asia or the South Himalayas have decreased significantly. And this pattern is often referred to as the South drying north-wetting pattern of precipitation change. And this change is dominated by change in precipitation in the summer. And accompanied with such a dipolar pattern of change in precipitation, other hydrologic cycle components has also shown similar changes. For example, in terms of lake volumes, observations over the past 4 decades have shown an expansion of lake area and volumes in the central and northern part of high mountain Asia. But the lakes over the southern part of high mountain Asia has shrinked. In addition, there is a significant glacial mass loss in the southern high mountain Asia in the past 2 decades. Because the high mountain Asia is an important water tower of the Asia, so the drying South Himalayas in the past could stretch the water supply to billions of people living here. So it is of vital importance to understand what has caused this south drying north-wetting pattern in precipitation. In particular, what are the roles of human activities and internal climate variability? And then looking into the future, will this drying South Himalayas continue into the future? To answer the first question regarding the relative roles of human activities and internal climate variability in the precipitation trend over this region, here we use multiple climate model simulations driven by different external forcings to disentangle the roles of different forcing agents and internal climate variability. So these include simulations forced by all forcings, which include both natural and anthropogenic forcings, and simulations forced by natural forcing only, greenhouse gas forcing only, and anthropogenic aerosols only. And we investigated to what extent the simulations under these different external forcings can reproduce a dipolar pattern of precipitation change compared to observations. And the results show that the dipolar precipitation change is primarily driven by anthropogenic aerosols. So how does anthropogenic aerosols work to affect precipitation change? We know that over the past few decades, there is a large amount of emission of anthropogenic aerosols in Asia. So this uneven emission of anthropogenic aerosols in Eurasia has resulted in a cooling trend over the lower latitude region and a weak warming trend in the north. So this inhomogeneous warming pattern induces a weakened meridional temperature gradient in the mid-latitudes, which further leads to a weakened westerly jet and hence a dipolar precipitation change. So we have shown that the anthropogenic aerosols is a main external driver for the dipolar precipitation change over high mountain Asia. But is that all the story? Let's look further at the temporal evolution of precipitation in this region. The left figure shows the precipitation change since 1950s over the northern high mountain Asia. So the precipitation in the northern part has increased steadily since 1950s. But over the southeastern high mountain Asia, there is a prominent interdecadal variation in precipitation. And this interdecadal variation also contributes greatly to the drying trend in the southeastern high mountain Asia in the past 2 or 3 decades. Then what is behind this interdecadal variation of precipitation? In fact, this is associated with interdecadal variation in the Pacific Ocean, which is often referred to as the interdecadal Pacific Oscillation. Then this interdecadal Pacific Oscillation affects the precipitation in the southeastern high mountain Asia by modulating the South Asian monsoon. In particular, in the late 1990s, the interdecadal Pacific Oscillation has undergone a phase transition from a positive to a negative phase. So this phase transition favors a recovery of the South Asian monsoon precipitation via atmospheric teleconnections, and which then further leads to a drying trend in the southeastern high mountain Asia. So to briefly conclude for the first question, what has caused the south drying north-wetting pattern? Firstly, the anthropogenic aerosol emissions in Asia is a main external driver. And upon that, the interdecadal Pacific Oscillation also contributes to drying South Himalayas via modulating the South Asian monsoon. Then looking into the future, will the dry in South Himalayas continue into the future? In fact, most climate model projections consistently show an increase in precipitation over the entire high mountain Asia in the far future. Then the question becomes why and when the precipitation over the high mountain Asia will change from a dipolar pattern to a monopolar wetting pattern. First, in terms of why, let's look at the precipitation response to greenhouse gas and anthropogenic aerosol forcing. The top rows show the precipitation trend on the greenhouse gas forcing in the historical period and in the future. And the greenhouse gas forcing favors a widespread wetting trend over both the historical period and also in the future. But in terms of the anthropogenic aerosols, its effect on precipitation is different from in the historical period and in the future. In the past few decades, because of anthropogenic aerosol emissions in Asia, it has led to a drying trend in southeastern high mountain Asia. But into the future, with the implementation of clean air policy and the reduction in anthropogenic aerosols, the weakened aerosol forcing will lead to a wetting trend in this region. So that is to say, the weakened anthropogenic aerosol forcing from the past to the future determines the transition point of the precipitation change in this region. And then when will the drying trend in South Himalayas change to a wetting trend? According to multiple climate model projections in the medium and high emission scenarios, at around 2040s, which corresponds to a global warming level of 1.9 degrees, the precipitation of the southeastern high mountain Asia will change from a drying trend to a wetting trend. And by that time, the signal of precipitation trend will emerge from the noise of climate internal variability. So to briefly summarize for the future change, under medium or high emission scenarios, the dipolar precipitation trend over the high mountain Asia is projected to shift into a monopolar wetting at around 2040s. And it is a reduction in aerosol emissions due to the implementation of clean air policies that determines the transition point of precipitation regime change. Okay, I'll stop here, and thank you very much for your attention.
Thank you, Wenxia. And the next speaker is Dr. Jing. She's from the Tsinghua University, and also she's worked for the Chinese Association for Science and Technology for the Future Earth Global Secretary China. Jing, please.
Okay. Thanks for the introduction and good afternoon. Mentioned minutes ago, China has promised to achieve carbon peaking by 2030 and carbon neutrality by 2060. So precise quantification of greenhouse gas emissions is demanding to make mitigation strategies and to monitor the progress to achieve this goal. Therefore, I will bring an up-to-date report of emission inventory in the last 4 decades. Okay, nitrous oxide is the third most important greenhouse gas and contribute 6% of the in 2022, its average atmosphere concentration reached to 335 ppb and is still increasing at a speed of 1.05 ppb per year. respectively. However, in China, natural sources only contribute 18.2% of total emission, while the other remaining 81% of N2O emissions come from anthropogenic sources. Agriculture accounted for more than 46% of the total N2O emission, among which about 22% come from fertilizer application in cropland, and 6.8% come from nitrogen mineralization. And industry, energy, and waste account for 15.5, 14.5, and 5.4% of the total emission and adipic acid production, electricity generation, and wastewater treatment are the individual largest N2O sources, respectively. The total N2O emissions in China increased from 229 to 2,000, from 889 to 2,291 GG N2O per year, and natural emissions steadily at a speed of 1.5 GG N2O per year. By the contrast, anthropogenic emissions increased by 235% in the last 4 decades. And agriculture is the largest N2O source. It accounts for 56.6% of the total anthropogenic emissions, and 66.7% of the total N2O increase in 1980 and 1990. However, Chinese government released the zero growth in fertilizer plan to control fertilizer usage in cropland, and afterwards, the agriculture source reduced at a speed of 20.5 GD N2O per year. By the contrast, waste N2O emission increased by 2.1 GD N2O per year. And after 2000, there is a dramatic increased demand for fossil fuel and adipic acid production. Therefore, the N2O emissions from energy and industry increased dramatically and exceeded agriculture to become the fastest increasing N2O source. And Chinese N2O emissions differ significantly across regions. The East was the largest regional N2O source, and the South was the smallest N2O source. Agriculture was the largest N2O sources in most regions except for the South, and natural sources, the largest natural sources was found in Southwest, and the largest industry, energy, and waste emission was found in the East. The East is not only the largest regional N2O sources, but also the fastest increasing N2O source. In the past decades, the N2O emissions from the East increased at a rate of 12.4 GG N2O per year, and the Central, the North, and the Southwest increased at a rate of 5.0, 5.0, and 4.8 GG N2O per year. As we know, activity data and emission factors contribute most of the uncertainties of the N2O budget. However, the above listed activity data can only be found in the literature or incomplete data set. Therefore, we suggest that with the growing demand of precise quantification of greenhouse gas emissions, these activity data related to greenhouse gas emissions should be included in national and provincial statistical data set. And according above result, we know that anthropogenic sources, including agriculture, energy, industry, and waste, dominate the N2O emissions in the whole country. Therefore, we suggest that mitigation actions should balance climate goals with food demand and economic development, such as improve nitrogen use efficiency by optimizing agriculture management and install N2O abatement equipment in adipic acid and nitric acid industry, and replace fossil fuel with green energy, and optimize waste treatment technique. That's all for my presentation. Thank you.
Okay, thank you, Dr. Wenjie. And now we have the next speaker is online. It's New Shuli professor from Chinese Academy of Science. So, are you ready, Shuli? Her? We can't hear the voice.
So can you hear me?
Yes, yes, thank you. Now, please, 2 minutes.
Okay, thank you. Okay. Good afternoon, everyone. Thanks, the organizers, very much for offering me this great opportunity. I would take this opportunity to introduce a global initiative on ecosystem restoration and carbon neutrality. We call it Global ERCAN. So what is Global ERCAN? It is an international cooperation program on big science plan. The science plan is to identify key research gap, opportunity, and priority areas for future research. The aim of Global ERCAN is to establish a dynamic global platform for international cooperation in ecosystem restoration and achieving carbon neutrality. So why do we need Global ERCAN? China and other countries in the world have set the climate-related goals to keep global warming within the 1.5 degrees centigrade threshold and avoid the worst impacts of climate change. To achieving that goal, terrestrial ecosystems play important roles. They can uptake carbon dioxide from the atmosphere by 30% of the human emissions every year. However, 25% of the world's terrestrial ecosystems are currently experiencing degradation, and it is expected that this proportion will increase by 75% by 2050. So the UNGS has proclaimed the UN decades, followed by over 70 countries. And more than 150 actions have been registered by UN Decade since the platform's launch in 2019. Actually, we have rich practices and experiences in ecological restoration, from the local to national and global scales. For example, at the global scale, we have the UNIPE Plant for the Planet program. And in China, we have a very famous 3 North Shelter Belt program. And actually, we have lots of the local restoration projects in China, like the Green Guangdong. Those ecosystem restoration actually have huge potentials for carbon uptake. It was estimated that the ecosystem restoration since the Industrial Revolution can up to 900 petagram carbon dioxide. And the right panel shows that even for grasslands, if we take some practices for ecosystem restoration, the soil carbon sequestration rate is very promising. For some forest-related projects, like reduced deforestation, afforestation, agroforestry, those measures together can account for more than 30 petagram carbon dioxide per year globally. And in China, in the past 2 decades, the ecosystem restoration totally accounted for 0.6 petagram carbon dioxide per year. And in the future 10 years and even 40 years, this number is also promising. So we have rich practice and studies on ecosystem restoration. However, when we did the literature analysis, we found that linking ecosystem restoration to carbon neutrality actually is very little. So we don't know what are good restoration practices for stable carbon sink, and what are the mechanisms underlying permanent carbon sequestration, and how to accurately assess carbon sink and manage the result carbon for policy making. Actually, there is currently no international scientific program specifically targeting ecosystem restoration and carbon neutrality. And we need an international network to coordinate research on ecosystem restoration for carbon dioxide removal. So we initiated Global Arcan. So what does Global Arcan do? We will do 4 things. One is practices. We will summarize the practices of ecosystem restoration for carbon neutrality. Using multiple approaches across multiple scales. The third one is mechanisms. We will study the process, study the ecological drivers for carbon sequestration in restoration. And the last one is management. We will improve the accuracy of accounting and carbon management during the ecosystem restoration. So specifically for the theme 1 practices, we will identify the good practices to help ecosystem restoration and carbon sink, and to quantify their effectiveness on carbon sequestration, and to develop indicator systems and technical methods for ecosystem restoration. For the theme 2 monitoring, we will develop the air, space, ground integrated observation systems for monitoring restoration. And we will track the dynamic changes in carbon sink during ecosystem restoration, and to reduce the uncertainty of remote sensing monitoring and model simulation. For the process understanding, we will review the biological mechanisms underlying carbon sink restoration, and understand the key factors and ecological processes driving carbon sinks, and to evaluate the long-term stability of carbon sequestration functions during restoration. And for the management, we will develop the process and standardize the carbon accounting methodology and build carbon sink management case banks for policymaking. And we also establish a conceptual framework for carbon sink accounting and management in restoration. So who will lead and supervise the Global Arcan? We have 2 co-chairs. One is Dr. Guirui Yu. He is the director of Chinese Ecosystem Research Network and China Flux. The other one is Werner Kuch. He is the Director of General of ECHOS. So we have 20 scientific committee members from 11 countries to supervise the progress of the global ocean. For the 4 research themes, for each research working group, we have one group leader from China and another one group leader from abroad. So the final goal of the global ocean is to share the methods and technologies for ecosystem restoration and to assess ecological restoration's role in carbon neutrality and to propose policies to accelerate carbon neutrality by sustainable ecosystem management. The output of the global ocean is to provide up-to-date knowledge on observation, simulation, and eco-processes, and to build a case banks and good practices for typical ecosystem restoration, and to help the policymaking and improve the public awareness by organizing international conference, workshops, and we also will strengthen the global partnership. So we look forward to the participation of more countries or regions to join the global ocean. That's all. Thank you for your attention.
And our next speaker is Zhang Qianggong. He's from the Northwestern Research Council of the Chinese Academy of Science. Qianggong, please.
It is my great pleasure to share our research and knowledge on cryosphere over the Third Pole region. Here is an outline of my presentation. The cryosphere is a part of Earth's surface with a certain thickness where temperatures are continuous at or below 0 degrees. It includes polar ice sheets, glaciers, sea ice, permafrost, and seasonal snow cover. The Tibetan Plateau and its surrounding regions hold the largest re-entry of cryosphere outside the polar regions, and are often referred to as Third Pole and High Mountain Asia. The Third Pole are also known as the Asia Water Tower, serves as the headwaters of many major Asian rivers, and recent research on global water towers show that there are 72 water towers worldwide, with 16 located in the Third Pole region. The Asia Water Tower are particularly important and vulnerable. The cryosphere observation network includes 17 comprehensive stations and 18 monitoring sites in the Third Pole region. Glacier change are a key focus of our research, with over 48,000 glaciers covering an area of more than 50,000 square kilometers. Almost all glaciers in this region are showing a shrinking trend, with the most rapid change observed in Himalayas, Tian Shan, and Altai. Since 2000, the total glacier mass loss has been estimated at negative 19 gigatons per year, and a clear acceleration in this trend has been observed after 2000. And this consistent and fast decline trend can be also evidenced by in-situ observations of some benchmark glaciers. We can take glacier number 1 at the headwater of Wenxia River in Tian Shan as an example, and this glacier has the longest observation history in China. The glacier has kept retreating since 1960s, and in 1994, the glacier broke up as 2 branches. Another example is Rongbu Glacier on north side of Mount Everest. We can clearly see the snow decreases on mountains, and glacier surface have been lowering. For permafrost, the total area for 2000 to 2016 is around 1.6 million square kilometers. The total permafrost area has decreased from 1960s to 2000. This can be also evidenced by active layer thickness, and currently the ALT was about 2.3 meters in the permafrost region, and the regional average ALT has increased with a rate of close to 2 centimeters per year. This means that the active layer has been deepening. Such warming of permafrost and deepening of active layer has resulted in widespread thermokarst formation that include soil slumps and thermokarst lakes. Snow cover in mountain regions have shown a decreasing trend in snow depths and snow cover days over the past 40 years, and this is particularly obvious in the southeastern part of the Tibetan Plateau. In summary, we have observed a comprehensive decline in the crossphere, including glaciers, permafrost, and snow cover over the Third Pole region. And this decline is primarily attributed to regional warming, which is occurring at a rate twice that of global warming. While wetting has been observed in most Third Pole regions, it cannot compensate for the warming-induced decline of glaciers. In addition to warming, I want to emphasize another factor, black carbon and dust, known as adsorbed impurities, can darken the snow surface and contribute to snow and ice melting. We found that BCM dust can induce 10 to 50% reduction of glacial albedo, and the relative forcing due to black carbon on glacial surface ranges from several watts per square meter to hundreds of watts per square meter. Black carbon can increase glacial melt by reducing glacial albedo, and it can also decrease precipitation, and therefore the BC actually poses a double effect on glacial melting. And Himalaya glaciers are most affected based on the simulation study. Next, we move to impact and hazards induced by cross-rate change. And first, let's see the impact on water resources. As per the IPCC report, peak water for high mountain Asia is projected to be around the mid-21st century. While take closer examination, it can be observed that in certain river basins, the peak water has already been reached or surpassed, with more rivers expected to reach peak water in the next few decades. Thawing permafrost can also affect river hydrology, and research indicates that a 40% coverage of permafrost serves as a critical threshold, and rare basins with extensive permafrost coverage will experience a relatively stable winter flow due to thawing permafrost input, but those with less coverage will have a decline in winter flow. It is important to note that the changing crossphere elements, including glacier, snow cover, and permafrost, will collectively impact runoff. For example, glacier retreating can increase summer runoff. Change of snow melt can advance spring flood peak, and thawing permafrost could increase winter runoff. The retreat of glacier has led to emerging issues related to glacial lakes and outburst floods. And currently, there are about 26,000 glacial lakes in Third Pole, and one-third of them being dammed by moraines. This means that these lakes are usually unstable. And one-third of all glacial lakes have high to very high hazard levels, and 1 in 6 glacial lakes will pose potentially high to very high risk to downstream communities. And glacial surge can result in sudden and severe hazard. We should notice that nearly half of the surge-type glaciers worldwide are located in the Third Pole region, with the Panmao and Karakoram serving as the two prominent centers. And here are some examples for several glacial surge events. The Chamli rock ice avalanche in the Indian Himalayas in 2021 had devastating effects, impacting areas up to 50 kilometers downstream and causing the destruction of facilities such as hydropower plants and bridges. While climate change-induced glacial surge was a core factor in this event, it is important to recognize that the geologic sighting, substantial vertical drop, and other unique features in the high mountain regions amplified the impact of this disaster. Additional cases occurred in western and eastern Tibet, including the twin collapse of Aru Glacier and the repeated collapse of Sedumpo Glacier during the 2010s. Aside from the surge activities, earthquakes and steep terrain can trigger and aggravate these disasters. While for snow hazards, there are 4 major types: snow melt flood, snow avalanche, snow drift, and snow disaster in pasturing areas. All of these are prevalent in Third Pole regions. Lastly, let's see what can we do to solve and mitigate this change and impact. Well, slowing and halting global warming are fundamental approaches to reducing the aforementioned impacts. Apart from this, I would like to emphasize that reduce regional black carbon emission could be an imperative and potentially effective measures. This will not only help to lower regional warming, but can also increase glacial albedo and therefore alleviate glacial melting. Some pioneer research experiments and attempts have been made to save glaciers. For example, researchers have tried to use geotextile to cover dark glacier, and this helped to reduce up to 34% of glacier melting in summer. And however, this method is only feasible for small actinic tourist glacier. Artificial snowing has also been applied in several glacier basins. The experiment in Musudao Glacier showed that 34% to 54% reduce of glacier mass loss. And in the India Himalayas, artificial glaciers such as ice reservoirs and ice stubbles have been created to conserve water for spring irrigation. To address cryosphere disasters and impact, we rely on more intensive observation and the development of early warning systems. Where certain hazards such as gloves, snow hazards, and soil slump hazards have been successfully predicted in specific locations, we should notice that glacier surges, glacier discharge floods, and ice and snow avalanches remain unpredictable, and we need to seek and develop more tools for mitigation in the future. That's all for my report. Thanks for your attention.
Thank you, Professor Zhang. And now we all 7 presentations finished. Now we have the time, 10 minutes for the discussion. We can have questions and from audience and all speakers. Any questions or comments, both from the in-person and online? I don't know, we can get some online questions?
I have a question for Dr. Zhang. I just want to know the warming level is compared to the pre-industrial or just a reference period, because you have a different warming period, and then precipitation pattern is going to shift from dipole to unified pattern. So what's the warming level is compared to which period?
Thank you for the question, Professor Zhai. I think it's compared to the recent past, because we know that at high emission scenarios, we will reach a 1.5 degree very immediately. So it's compared to recent past.
Thank you so much.
And there are the comments or questions. This afternoon, I see a lot of people, hundreds or thousands of people, is march for climate justice and also climate adaptation. I think they are very busy for the march, so they forget we have our side events here. I think they are still with. So, may I ask questions for the Panmao? What's the idea for the IPCC 6 on the climate justice and the climate adaptation?
Well, that's a good question.
Yeah.
For working group 1, actually mainly focus on science, but in this report, there are contents about the justice and issue. Say they provide a figure in the thesis report in the summary for the policymakers. You see a figure related to the vulnerability issue and the per capita emission, for different regions and countries. You see, normally the most vulnerable people, they contribute the least to the emission of the greenhouse gases. I think that's tells us, that's most rich people, most the developed world contribute more, but they have less vulnerability to the global warming, the climate change issue. I think so. IPC really, try to tell something about the people and how to, to address the justice issue. Thank you so much.
Okay, thank you, Panmao. And another question raised from the march, it's very interesting. Many people crowd and shouting for the climate adaptation and climate justice, and using some people dancing and singing, and it's very interesting. But for the another questions for the Professor Jiang Tong, in IPCC Air 6, even I think for the coming Air 7, they will use the shared social economic pathways, SSP. And you now mentioned from SSP to SAP. It's from shared adaptation pathways, not SAP. Now my questions, you see, hundreds of thousands young men come to the street and come to the meeting all around the march for the adaptation. If it's possible for your SAP, share the adaptation pathways to somehow can substitute the SSP in future, or both SAP and SP work together for a long time.
Yes. First, we should know the mitigation and adaptation both are addressing reduction of the impact of the climate change risk. Yeah. But most people interesting, or society interesting to mitigate it, climate change. They are no interesting for the adaptations. We should, as we know, mitigation only can reduce the frequency of the hazards. But mitigation do not reduce the losses. And adaptation can be reduce the losses and damage, and via the changing of the exposure and vulnerability. So the people must continually working for to promote the adaptation and to reduce the losses. As some cases say that if the current adaptation could not solve our future losses of food security, even if we use limited adaptation, cannot help for the reduction of the food security. But we should more investment for the moderate and extensive adaptation can keep the future next 50 years our food security. So that means more adaptation, more secure of our food security. So we should, even if all of us, we should promote our adaptation for each person's, and we can do for this.
Yes, thank you, Professor Jiang. I see Jiang, put your hands. You have questions. But before you ask me questions, I ask you one questions. Jiang is Dr. Zhang Jiang is from the National Climate Center of China, and she is always the member of the party of Chinese delegation. So my question is, do the UNFCCC COP28 have some response or answers to the climate justice and climate adaptation? This afternoon, thousands of young young people, come there shouting and grinding for the climate adaptation and climate justice. And what's the UNFCCC COP28 give the response for the young man's desire?
Okay.
Yeah, thank you. Yeah.
Thank you, Professor Zhang, for your question. Actually, for COP28, it's more or less the same as previous COP, because we are coming here to solve the climate issues by establish the global climate change governance framework. And after 30 years of all this negotiation, we have milestones. Of course, there are a lot of challenges there. For COP28, I think the main item is global stocktake. If we say stocktake, that means we need to list all these issues to check what we have got and what we lost. And this is what we are here trying to solve the problem with look backward and look forward. This is what we are doing. Actually, for your the especially agenda item you called climate justice and response measures with climate change. This is very, essential and important issue when we're dealing with climate change. We know climate change is a long-term issue. We have historical responsibility on this one, and we are emitters at this moment. So it's very important to have a very clear logic on this one. So who need to take lead and who need to do more ambitions, implementation on these issues. This is what we are here to negotiate. And I should say the process is not so smooth. We are still like debating among each others. So, and I think the cheerful things for us is to see how young generation are participating in this process. They give their voice and their stage, and I think they will be very, very good actors in future to dealing with climate change. Of course, this is my answer to your question, and also I have comments on this session. First, thank you so much to organize this session, to invite so many experts here to share their views and works on climate change. It's very important and valuable work to let the world know how Chinese scientists work on climate change. I think the topics including physical science and the impact of climate change and the future pathways, which Professor Jiang just made intervention on that one. Actually, this is due to the, I just have 1 minute, okay, 1 minute. So due to so climate change is governance on climate change is not a simple issue. You need to connect from physical science to social, economic, and all these things together. So I want to ask you a question about how you think about how to link all those different aspects into a system to solve the problem with a holistic manner. Thank you.
Okay, thank you very much. I think it's hard for me to answer the questions. Maybe Panmao, you can do it.
You have a model, you already have a sheet.
Yes. But I think for this question, the model is not enough, not good enough for answer such questions. Now, in the for six models, we had different group. One group in the work group 3 worked on the climate and economy, something like that. And in the first group, we have the Earth system model. But the two models, human activities and the natural Earth system, the different, divided into two groups. This is something, really challenging for to answer your questions. It's to try to link the human societies and the natural systems, and also we have the policy, adaptation and mitigation. So it's very complicated. I think, I don't know, maybe AI. I don't know if AI do something like that.
Yeah, I think AR6 used SSP already link the physical science to the socio-economic pathways. I think that's a good start.
Okay, thank you very much, Jiang. Thank you. And now, questions? Okay, please. One more, yeah.
这是澎湃记者，
Oh, this is from Panmao, yeah.
还是40 minutes，只有40分40
Ladies and gentlemen, the time for the session has come to an end. Thank you.
结束，回来见。
Okay,
Okay, thank you so much.
thank you very much.